Action. Good morning, everyone. I'm Haoyang, a fifth year PhD student from Central South University, and today I'm going to present our work on introspective congestion control for consistent high performance. It's a congestion control meaning worked in the internet. In modern networks, congestion control plays a crucial role in maintaining high transmission performance. Uh, However, congestion control faces significant challenges due to the network variability, including bad flex restrictions, round trip time changes, and the random packet loss. What's worse, these challenges are further exacerbated by diverse applications, which have become more and more sensitive to the transmission performance. So to address these challenges, existing thesis has evolved from purely respond to congestion events to proactively inferring the past conditions like best RTT and BDP. However, these methods are not always reliable. Sometimes they fail to make accurate inference, resulting in performance degradation. To approach the above problem, we introduce a projection-based introspective method to design congestion control. The core idea behind this method is to introspect whether the inferred past conditions are credible and customize flexible proactive actions to make correct past condition inference. This can ensure high performance even in dynamic and unpredictable network environments. So this paper mainly makes the following key contributions. We propose a projection-based introspective method and design a congestion control algorithm ICC based on this method. And we implement ICC in different platforms and do wide evaluations. So here I want to introduce our design philosophy. Um, well, we realized that past condition inference provides the baseline for judging and responding to congestion across device network environments. Recently, COPA and BBR infer past conditions in their own different ways. On the one hand, COPA proactively scouts its profile of AIAD rates adjustment rules to such that the bottom link buffer is joined periodically and for the inference of base RTT. On the other hand, BBR probes BDP via its probe RTT actions and the probe bandwidth actions. However, this inference often fail, when specifically their past condition inference are always trusted, but when the actual past conditions are changed, the inference might become stale soon. Moreover, their preactive actions to infer the past condition inference may not take effect as expected. On the one hand, the fixed actions may not take effect in certain cases, and this is proved in the previous works. And on the other hand, the inference might be disturbed by the actions themselves. And sorry. What's worse, to addressing this challenge is further complicated by two key constraints. That is, the inference of past conditions should not harm the good performance of the CC itself, and we think currently there is not not sufficient information to do such things. Therefore, we try to seek a way to extract sufficient information without harm the good performance of congestion control. We conduct a simulation where networks is changed at 10 second and 20 second. Observing the wavelets transform of the bottleneck queue size, we find that there is a great difference among different stages in the wavelet spectrum, wherein some spatial spectra are only exhibits if only the network keeps unchanged. Specifically, the profile of asymmetric MIMD rate adjustment rules of BBR is projected as multiple brightened horizontal lines in the wavelet spectra, and meanwhile the symmetric AIAD rules of COPA is projected as one single brightened horizontal line. So in this way, the information of whether network keeps unchanged and how proactive actions work could be implied by the projection. Moreover, as both profile and projection are accompanied by the rate adjustment rules of congestion control, there is no any extra operations to or potentially break the good performance. Based on the above insights, we propose the projection-based introspective method, which introspects from the projection of profile for credible past condition inference and consistent high performance. First, we introspect whether the past conditions are unchanged. We suggest to sculpt a unique profile rate adjustment rules like COPA, then monitor its projection to introspect whether the past conditions are unchanged. Moreover, as the pattern similar to projection may be monitored by accident, we conduct continuous monitors to avoid this misleading, this method is effects proved in the appendix of our paper. Second, we then introspect whether the customized proactive probe actions take effect as expected. The proactive probe is only activated when the past conditions remain unchanged. In such a case, the variation of the congestion system is mainly determined by the rate adjustment itself. Therefore, the proactive probe actions is controllable and can enforce the congestion system working at the proper region to facilitate the past condition inference. Once the proactive probe actions is take effect, the inference is regarded as credible and updated. Based on the above two introspection, congestion control can extract more information for getting credible past condition inference, correspondingly achieves better performance. If the credible past condition inference are temporarily not available, we suggest a fast response module to provide the best performance guarantees without credible inference. Based on the projection-based introspective method, we design algorithm ICC. The framework of ICC is simple but effective. First of all, ICC controls both sending rates and congestion window by responding to delay signals. And the ICC meaning contains four modules. First, ICC sculpts its unique profile with symmetric roles. And second, the projection of this profile is monitored via conducting FFT to the time series of delay signals. Third, once the projection is monitored continuously, ICC will regulate coefficients lambda to proactively probe the best RTT and the bottleneck wise C/flow number and last, ICC fast respond to congestion with the help of previous credible inference. The profile sculpting has two design goals. On the one hand, the sculpted profile should correspond to a distinct projection. For example, the single brightened horizontal line in the frequency domain is good. Therefore, ICC conducts symmetric rate adjustment rules like this. On the other hand, the profile of ICC corresponds to good performance with bounded queuing delay and high throughput. ICC utilizes FFT to monitor the projection of profile in the frequency domain. The monitor is a continuous process that avoids the misleading by accident. By the way, the reason for utilizing FFT here instead of wavelet transformation is to reduce computational overhead. When the projection of profile is distinguished concentratively, ICC conducts proactive probe action that is regulates lambda for the correct path condition inference without breaking the profile. Specifically, lambda is related to the amplitude of the oscillation. To find a proper value of lambda to join the queue but not hurt the throughput, lambda is regulated with these AIMD rules. Last, when path conditions are changing and hard to infer, ICC responds to the variation fast via regulation of coefficients theta. This mechanism is similar to COPA. Moreover, as the current inference is not credible, ICC will inherit the previous inferred best RTT and bar lambda for better response. ICC also contains a competitive mode for coexisting with buffer filling schemes like cubic. We theoretically proved that ICC can rapidly and smoothly converge to the equilibrium point. Meanwhile, ICC maintains high performance during the whole convergence process, resulting in consistent good performance. The corresponding details are presented in the appendix of our paper. To evaluate ICC, we implement it on NS3 Linux user space and Quick. The evaluated scenarios across the simulations, emulations, real world, and production platform. Moreover, ICC is compared against several other schemes, including Cubic, BBR, and so on. First of all, ICC shows remarkable properties. First, ICC oscillates symmetrically around the desired equilibrium point, maintaining low queuing delay as expected. And ICC can maintain its high throughput and small bounded queuing delay with different parameters. This proves that ICC successfully sculpts its profiles and project it to the system. Moreover, ICC benefited from it. ICC can consistently infer path conditions that like C/N and best RTT. Then we test the ICC in diverse scenarios to verify its high performance. ICC has good fairness no matter facing dynamic traffics or heterogeneous links. Uh, and ICC is also robust to random loss and friendly to TCP. Moreover, ICC show good performance over links of wide BDPs. We also test the ICC in real-world environments. Uh, the test in internet contains cloud loads across different continents. Um, in multiple repeated tests, ICC consistently maintain high performance, and ICC also performs well in cellular links, satellite links, and even data center. We also ICC is also tested under the productional scenario of Alipay. User testing at the scale of hundreds of thousands participants demonstrates that advantages of ICC, especially in terms of queuing delay. So, in conclusion, we believe that past condition inference is a powerful tool for congestion control, enabling it to adapt to diverse network environments. However, introspection is essential as the inference might sometimes be inaccurate. So we propose a method for introspection, which focus on the profile and the projection. They can simply provide some extra information for introspection, and we put the method into practice with sculpting a unique profile and monitoring its projection in frequency domain. While this is one effective way to achieve introspection, we anticipate that other methods may be further explored in future research. That's all. Thank you. Thank you for listening.
So, questions?